Welcome to a 3x3 example with eigenvalue of multiplicity 2. Again, we're focusing on with eigenspace dimension 1. So just recall, if we have y prime equaling a times y, a 3x3 with eigenvalue lambda 1 equaling lambda 2 and eigenspace dimension 1 spanned by eigenvector xi or xi1. Then y1 equaling xi1 times e to the lambda 1t and y2 equaling in parentheses xi1t plus eta 1 close parentheses times e to the lambda 1t. Here where a minus lambda times the identity times eta 1 is equal to xi1. These two vectors are, or solutions are linearly independent. So our job here is to find the general solution to the 3x3 system. Y prime is equal to first row 1 0 0, second row 1 -5 3, third row 2 -3 1, all multiplying y. So our very first step is to go ahead and find the eigenvalues. So we are looking at the determinant of 1 minus lambda 0 0, 1, and then -5 minus lambda 3, and then 2 -3 and 1 minus lambda. And then all of this determinant should be equal to 0. So just note, since that first row only has one non-zero term, we can use that first row for finding our determinant. This is just, the determinant is just 1 minus lambda times the determinant of -5 minus lambda 3 for our first row, and -3 1 minus lambda for our second row, and then the rest we would have a -0 and +0 for the other two subdeterminants, since they're being multiplied by 0. All of this should be equal to 0. So we are looking at 1 minus lambda times -5 minus lambda times 1 minus lambda minus -9. And that all should be equal to 0. So this is 1 minus lambda times lambda squared. Then we have plus 5 lambda minus lambda becomes plus 4 lambda. And then we have a -5 and a +9 is +4. So we are looking at 1 minus lambda times lambda squared plus 4 lambda plus 4, or 1 minus lambda times lambda plus 2 squared is equal to 0. So we have lambda 1 is equal to 1. And we have lambda 2 and lambda 3 are both -2. So we're going to have to find eigenvectors for both cases in the case with lambda 2, we will likely also have to find an eta. So step 2 is find the eigenvectors. Just taking a moment to update. There we go. So we'll find the eigenvectors. So let's do lambda 1 equaling 1 first. So we are looking at 1 minus 1, 0, 0 for our first row. Then we have 1, negative 5 minus 1, 3 for a second row. And for our last row, we have 2, negative 3, and 1 minus 1. I apologize for the jumping of the screen. So 2, negative 3, and 1 minus 1 for our last row. And this is multiplying psi, hopefully getting, or to get 0. I need to update my screen. Oh, there we go. It's updated. Again, I apologize for the jumping screen. So for our augmented matrix, we're looking at a first row of 0, 0, 0 with augmentation 0. A second row of 1, negative 6, 3. And a last row of 2, negative 3, 0. Augmentation 0 in both of those rows. If we do leave row 1 alone, 0, 0, 0. Leave row 2 alone, 1, negative 6, 3, 0. And then in row 3, if we do 2 times row 1, 2 times row 2 minus row 3, then we would have 2 minus 2 is 0. Negative 6. We would have we'd have negative 12 plus 3 is negative 9. And then we would have 6 minus 0 is 6. And 0. We could, if we wanted, rescale this. You don't have to do either of these steps if you don't want. Since we do already have a free variable, and it's clear that the other two rows are not multiples of each other, but we have 1, negative 6, 3, 0 for our first row. If we do row 3 divided by negative 3, we can scale it a little and have 3, negative 2, 0 for row 3. So we have a free variable. We know that psi2 is 3 times psi2 is equal to 2 times psi3. So what I would do is I would pick psi3 to equal 3. Then that means that psi2 is simply equal to 2. And then we know that psi1 minus 6 psi2 plus 3 psi3 is equal to 0. So we are looking at psi1 is equal to 6 times 2 minus 3 times 3. Or in other words, psi1 is equal to 3. So we have for our eigenvector psi1 corresponding to lambda 1 equals 1. We get the vector 3, 2, 3. For lambda 2 equaling lambda 3 equaling -2, we are looking at the system. We have 1 minus -2, 0, 0. For our second row, we have 1, -5 minus -2, 3. And for our last row, I apologize for the scrolling. For our last row, we would have 2, -3, 1 minus -2. This is multiplying some vector xi to get the 0 vector. So we are looking at the augmented matrix 3, 0, 0, 1, -3, 3, and 2, -3, 3. Sorry, and then with augmentation, 0 vector. So going from here, this becomes, if we do row 3 divided by 3, we just have the row 1, 0, 0, augmentation 0. If we do sorry, that should have been row 1 divided by 3, not row 3 divided by 3. Row 1 divided by 3 gave us 1, 0, 0, 0. If we then do row 1 divided by 3 minus row 2, that would just cancel off the 1 in the first position, since we would be looking at 1 minus 1. Then we have 0 minus -3 becomes 3. And 0 minus 3 would be -3, and then 0. So our second row is 0, 3, -3, 0. If we do 2 times row 1 divided by 3 minus row 3, that would be 2 minus 2 is 0. 0 minus -3 is 3. And 0 minus 3 is -3, and then 0. So now our second and third row are identical. If we finish this up, we have 1, 0, 0, 0. Our second row, let's go ahead and do row 2 divided by 3. That will give us 0, 1, -1, 0. And then if we just do row 2 minus row 3 for our last row, that will give us all zeros. I'm gonna pause and update my screen. So continuing from here, we have one free variable. We also have that xi1 has to be equal to 0. And we have the xi2 should be equal to xi3. So we might as well pick xi2 to be equal to 1. We have that xi3 is also 1. And so we have the our vector xi2 can be chosen to be the vector 0, 1, 1. Last up, we need to find eta. So our next step is, since we only had eigenspace of dimension 1, for eigenvalue of multiplicity 2. Then what we need to do is we need to find eta. So we have A minus lambda I, so minus -2. Oh, let's do A minus lambda I first. A minus lambda I times eta should be equal to our psi 2. So we are looking at A minus -2 times I times our eta should be equal to the vector we just found, which was 0, 1, 1. That A minus -2I we were just working with, A minus -2I is precisely the vector or the matrix we used for finding the eigenvectors for lambda 2 equaling lambda 3 equals -2. So we had 1 minus -2, 0, 0. Then we had 1, -5 minus -2, 3. And then we had 2, -3, 3 minus, 1 minus -2. Let me just verify I have that correct. So 2, -3, 1 minus -2. Yes. So this is multiplying our eta to get 0, 1, 1. Then we are looking at 3, 0, 0, 0 for our first augmentation. 1, -3, 3, 1 for our second augmentation. And 2, -3, 3, 1 for the last augmentation. So if we reduce this, if we do row 1 divided by 3, again, we are looking at 1, 0, 0, 0. If we do row 1 divided by 3 and then subtract off row 2, we are looking at 1 minus 1 is 0. 0 minus -3 is 3. 0 minus 3 is -3. And 0 minus 1 is -1. And then if we do 2 times row 1 divided by 3 minus row 3, again, we would have 2 minus 2 is 0. 0 minus -3 is 3. And 0 minus 3 is -3. And 0 minus 1 is -1. So if we leave row 1 alone, 1, 0, 0, augmentation 0. If we now do row 2 divided by 3, we will have 0, 1, -1, -1. And if we just do row 2 minus row 3, we will then have 0, 0, 0, 0 for our last row. So once again, we have a free variable. We know that eta 1 has to be equal to 0. And we have eta 2 minus eta 3 is equal to -1. Now, because that right-hand side is no longer 0, we can go ahead and pick one of those to be 0. So let's go ahead and pick eta 2 to be equal to 0. And that means that eta 3 must be equal to 1. And so we have our eta is the vector 0, 0, 1. So let's go ahead and find our fundamental set of solutions and then find the general solution. So our fundamental set of solutions we will have y1 was psi 1, which if I remember correctly was 3, 2, 3 times e to the lambda 1t, and lambda 1 was 1, so we have e to the t. I'm just going to verify I remember that correctly. yes, xi1 was 3, 2, 3. You could come up with any scalar multiple of that and it will still be completely correct. Our y2, we found the eigenvector 0, 1, 1. Our lambda was -2, so we will multiply by e to the -2t. For y3, we will have eigenvector from lambda equaling -2, so 0, 1, 1, multiplying t, plus the eta we found, 0, 0, 1. And that whole thing multiplying e to the -2t. So we can rewrite y3 as 0 times t plus 0 is just 0. And then we have 1 times t plus 0 is t. And then we have 1 times t plus 1 is t plus 1. So we have 0 t, t plus 1, all multiplying e to the -2t. Last up, we find our general solution. We have y is equal to c1 times 3, 2, 3 e to the t plus c2 times 0, 1, 1 e to the -2t plus c3 times 0 t, t plus 1, all multiplying e to the -2t. So this is solving a 3x3 system where we have a repeated eigenvalue of multiplicity 2, but the corresponding eigenspace only has dimension 1. In the next video, we will look at the case where we have repeated eigenvalue of multiplicity 3.